And today we will read Pradeep Volume 3 Electronic Spectra. Introduction. It has been discussed in the last chapter that when molecule absorb energy in the microwave region, far infrared region, transition between the rotational level takes place giving rotational spectra. Similarly, if the energy is absorbed in the near infrared region, transition take place between the vibrational level accompanied by those in the rotational level, giving vibrational rotational spectra. However, if the light is absorbed in the visible region or ultraviolet region, electronic transition takes place given electronic spectra. A number of other processes also takes place on absorption of light called photoprocesses. These may be photophysical processes such as fluorescence and phosphorescence or photochemical reaction. The branch of science dealing with such process is known as photochemistry. In the present chapter, we shall take up briefly an electronic spectra, whereas photochemistry will be discussed in the next chapter. Just as there are electronic energy level in an atom, there are electronic energy level in a molecule also. However, there are no simple formulae available for the energies of these electronic level, except for hydrogen-like atoms. Electronic spectra are obtained when the electron and a molecule are excited for a lower electronic energy level to a higher level. However, as the electronic transition is accompanied by vibration and rotation transition, the total energy of the molecule in any state is the sum of electronic energy, vibration energy, and rotation energy. If EV, and ER represent the electronic energy, vibration energy, and rotation energy respectively of the molecule in the initial state before transition, and E dash, EV dash, and ER dash the corresponding values in the final state after transition. Then we have energy of the molecule in the initial state. E is equals to EE plus EV plus ER. Energy of the molecule in final state. E is equals to EE dash plus EV dash plus ER dash. Equation 2. Therefore, energy change involved in the electronic transition will be given by delta E is equals to E dash minus E is equals to EE dash plus EV dash plus ER dash minus EE plus EV plus ER is equals to EE dash minus EE minus EV dash minus EV plus ER dash minus ER is equals to delta EE plus delta EV plus delta ER. हाँ मम ओके ठीक है. But according to Planck's quantum theory, delta E is equals to h nu is equals to h c nu bar. H c nu bar is equals to delta EE plus delta EV plus delta ER. V bar is equals to delta EE plus delta EV plus delta ER divided by h nu. Equation 4. As for particular electronic transition, so that delta EE remain constant, and for particular vibrational transition, so that delta EV remain constant. Delta ER can have different values, but due to different rotation transition within the same vibration energy, change in the same electronic energy, a number of closely spaced lines are obtained. This constitutes a band. For each vibrational transition, separate band will be obtained. Thus, due to different vibrational transition for a particular transition, a set of band is obtained called the band group or band system. Each electronic transition will give a band system, and hence the complete electronic spectra involving different electronic transition give rise to a series of band group. Thus, the electronic band spectrum obtained for a gaseous molecule is quite complex. In spite of the complex nature of the electronic band spectra, these are preferred over the other types because these are obtained in the visible and ultraviolet regions, so that these can be easily photographed and studied. 3.52.2 Calculation of dissociation energy of molecule. A study of the electronic band spectrum reveals that at the end of the spectrum, the distance of separation between the lines becomes smaller and smaller till ultimately the line spectrum vanishes and space of continuous emission starts. The frequency corresponding to the point where the line spectrum vanishes is the frequency necessary for dissociation of the molecule into atoms. Thus, electronic band spectrum can be used not only for getting the information as given by the vibrational rotational spectra, but it can also be used in evaluating the dissociation energy of the molecule. 3.53 Potential energy curve and Frank Cordon principle. The explanation of the electronic band spectra and dissociation energy can be easily understood in terms of potential energy curve and Frank Cordon principle as follows. The potential energy curve of a diatomic molecule is obtained by plotting the potential energy of the system versus internuclear distance between the two approaching atoms. The curve obtained is of the shape shown in figure 3.38. However, even at the minimum energy position, equilibrium position, represented by point x, the atoms are vibrating so that the internuclear distance keep on changing. Therefore, the potential energy keeps on oscillating about the minimum position. The vibrational level thus occupied by the system may be represented by horizontal lines and indicated by appropriate vibrational quantum numbers. If sufficient energy is supplied so that system occupies a vibrational level represented by Vd, the corresponding internuclear distance should become infinity. That is, the molecule should not dissociate into atoms. However, this usually does not happen because of the before the stage is reached, the electron jumps to the higher energy level, that is, electronic transition takes place and dissociation will take place only for the molecule in the higher energy level. Now, every electronic state has its own potential energy curve. Two such curves for the lower electronic state are shown in figure 3.39 by 1 and 2 respectively. They differ in the fact that the minimum of the potential curve for the excited state 2 is at larger internuclear distance than the ground electronic state 1. The dissociation energy for the two states are different as shown in figure 3.39, that is D2 is smaller than D1. This is evidently due to the fact that bonding in the excited state is weaker than in the ground state. The vertical distance between the minimum of the two curves gives the difference between the electronic energy of the two states, is shown in the figure 3.39. The transition between the two electronic states takes place according to the Frank-Cordon principle explained above. According to this principle, nuclei being much more massive than electron, and electronic transition takes place much more faster than the nuclei can oscillate to change their internuclear distance. An electronic transition takes place from an extreme end of a vibrational level, example from A or A dash is shown in figure 3.39, because the velocity of the atom is zero at these positions and they spend maximum time at these points. As internuclear separation remain the same, the transition can be represented by a vertical line, example from point A dash to point C of the upper curve, and not from the potential energy minimum of lower curve of that upper curve. The new vibrational level must be one with the nearest to the point C. Counting level, it appears that the excited molecule will be in third or fourth vibrational level of state 2. This explains why in the electronic transition there is no simple selection rule for the transition among the variation level. All type of transition from lowest vibrational level to any kind of vibrational level of higher electronic state are possible. It may be mentioned that according to the quantum mechanics, the transition from the lowest level mu is equals to 0 takes place from the midpoint of the vibrational level, which is the equilibrium or the most probable position, and not from the extreme positions. Each vibrational level has a large number of very closely spaced rotational levels which have not been shown in the diagram. Now, when the transition takes place from vibrational level of the lower electronic state to some vibrational level of the upper electronic state, it is accompanied by a number of transitions between the rotational levels. The result is a group of closely spaced line called a band. Since a number of vibration transition takes place, a group of band called the band system is obtained. Further, the transition takes place between many different electronic states. The result is electronic band spectrum consisting of several band systems. If electronic transition similar to A-C takes place, the result in an absorption spectrum consisting of a number of vibration bands. If, however, a transition similar to BD takes place, where D represents the vibration level corresponding to which the internuclear distance is infinity, the molecule dissociates. Thus, when such a transition takes place, the absorption spectrum consists of a number of bands corresponding to the transition from the ground state to definite vibrational level in the upper state. But this band will converge and finally pass into a continuous region or continuum which has no fine structure. The point at which the continuum starts is called the convergence limit. The frequency and hence the energy corresponding to this limit gives the dissociation energy of the molecule. However, it is important to note that after dissociation, atoms are produced in the electronically excited state and not in the ground state. Hence, to obtain the energy of dissociation into ground state atoms, the excitation energy of the atom must be subtracted. Lastly, it may be pointed out that if the minimum of the upper electronic state is nearly at the same internuclear distance as that of the ground electronic state, the transition from V is equals to 0 of the ground state to V is equals to 0 of the upper state, that is 0 minus 0 transition, is the strongest. 3.54 Electronic spectrum of a diatomic molecule. As shown in figure 3.39, in case of diatomic molecule, when a photon is absorbed by the molecule, most of probable electronic transition that takes place according to Frank-Cordon principle is from B is equals to 0 of the lower electronic state to V is equals to 2 of the higher electronic state. This is called 0 to rho transition. Other transition from V is equals to 0 level of the ground electronic state to different vibrational level of the excited electronic state also takes place, but with much lower probability. Thus, the transition 0 to 2 has the maximum intensity, whereas the other transition have smaller intensity. The result is a spectrum of the type shown in figure 3.40. The other transitions from V is equals to 0 level to ground level electronic state to different vibration level of excited electronic state also take place, but with much lower probability. Thus, the transition 0 to 2 has the maximum intensity, where the other transition have smaller intensity. The result is a spectrum shown in the figure 3.40. 3.55 Selection rules for electronic transition in molecules. In order to understand selection rules for electronic transition in molecules, we should first understand a few terms and symbols to be used therein. First, parity. Parity represents the behavior of an orbital with respect to inversion. It is used for molecular orbital of homonuclear diatomic molecule. We consider a point in the molecular orbital and in not the sign of the orbital. Wave function. Then we travel equal distance through the center of the molecule to a point, center of inversion on other side. This operation is called inversion. If at a point the orbital has same sign, it is said to give even parity and is denoted G from Girard. German word for even. If the orbital has opposite sign, then it is said to have odd parity and is denoted by U, uneven. The parity designation apply only to homonuclear diatomic molecules because heteronuclear diatomic molecules like HCl do not have a center of inversion. As shown in figure 3.41 below, a bonding orbital has even parity and is written as sigma G, a sigma star orbital, and has odd parity and is written as sigma U. A bonding pi orbital has odd parity and is denoted as sigma U, and a sigma star orbital has an even parity denoted as sigma G. Second is multiplicity of state. The ground or excited electronic state of any species may have one or more unpaired electron with spin in the same direction or opposite direction. If S represents total spin quantum number, then 2S plus 1 gives the spin multiplicity of the state. If S is equals to 0, multiplicity of the state is equals to 1. It is called singlet state. If S is equals to half, multiplicity is equals to half. 2 into half plus 1 is equals to 2. It is doublet state. If S is equals to 1, multiplicity is equals to 3. It is called triplet state and so on. For example, in the ground state, H2 positive has only one electron. Multiplicity is equals to 2. Similarly, O2 molecule in the ground state have two unpaired electrons with parallel spins. Its multiplicity is equals to 3. Third, term symbol of molecules. These symbols give complete information about the state of the molecule, that is, orbital angular momentum, multiplicity, and parity. Depending upon the component of the total angular momentum about internuclear axis, there are given symbols as summation, delta, etc. The above symbols multiplicity is added on the left as a superscript and a parity is added to the subscript on the right. For example, first, the single electron H2 positive in sigma molecule orbital has zero orbital angular momentum, hence the term is summation. Further, it has multiplicity is equals to 2 as explained earlier, and then parity of the unoccupied orbital is G star. Therefore, full term symbol is 2 sigma G. The term symbol for any closed shell homonuclear diatomic molecule is 1 sigma G because the spin is 0. As the all electrons are paired, there is no angular momentum for closed shell and the overall parity is G. In case of O2 in the ground state, the 2 pi electron occupy different orbitals with parallel spin and overall parity of the molecule is equals to closed shell into G is equals to G. Hence, the term symbol is 3 summation G. Lastly, a superscript plus or negative on a summation term symbol is added to show the behavior of the molecular wave function on reflection in a plane containing the nuclei. In case of O2, one electron is in 2 pi x, which changes sign on reflection in the yz plane, and other in the 2 pi y, which does not. The overall reflection symmetry is therefore closed shell into plus into minus is equals to minus. Hence, the full term symbol is 3 summation minus G minus. Now we give below the selection rule for transition between different state of molecule. First, only transition are allowed between the state for which difference in the component of the orbital angular momentum along z-axis is equals to 0 or plus 1. Thus, summation, delta summation is not allowed. The transition are not allowed between the states having same multiplicity. Thus, singlet and triplet transition may occur, but singlet triplet transition are forbidden. Summation positive minus to summation positive and summation negative to summation negative transition are allowed, but summation positive to summation negative are not allowed. Only those transitions which are allowed which are accompanied by a chance in parity. Thus, G to U and U to G is allowed, but G to G and U to U are forbidden. This is known as Laporte's election rule. 3.56 Molecular orbitals sigma, pi, n involved in electronic transitions. The most common molecular orbital present in a molecule are the bonding molecular orbitals sigma and pi, and the corresponding anti-bonding molecular orbital, that is sigma star and pi star. Beside these, there may be heteroatoms such as N or O present in the molecule which have orbitals containing lone pair of electrons. As they are non-bonding orbitals, these are designated as N orbitals, which do not have any corresponding anti-bonding orbitals. In case of the homonuclear diatomic molecules such as H2N2 etc., the highest occupied molecular orbital HOMO in the ground state is a bonding molecular orbital, whereas the lowest unoccupied molecular orbital LUMO is an anti-bonding molecular orbital ABMO. The electronic transition takes place from HOMO to LUMO on absorption of suitable energy, usually the shorter wavelength part of the ultraviolet region. The transition may also take place from n orbital to the anti-bonding molecular orbital. In other words, the electron may be excited from sigma, pi or n orbital to sigma star and pi star orbitals. Thus, transitions which are allowed are sigma to sigma star, pi to pi star, and n to pi star or n to sigma star. This type of transition involved depend upon the nature of the compound and takes place by absorption of frequency characteristic of the compound of the ground present. Taking the example of carbonyl compound aldehyde and ketone, the sigma, pi and n orbitals are excited as shown in figure 3.4.2. Thus, the transition takes place r n to pi star at lambda is equals to 280 nanometer and pi to pi star at lambda is equals to 180 nanometer. Further, it is interesting to point out that if a single electron excited from the lower orbital to find excited antibonding molecular orbital has a spin opposite to that of the electron left in the lower orbital, figure 4.3.43a, the total spin of the excited state is s is equals to 0, so that multiplicity is equals to 2s plus 1 is equals to 1. Hence, the excited molecule will be in singlet state. If two electrons in the upper and lower orbitals have parallel spins, figure 3.43b, s is equals to half plus half is equals to 1, so that 2s plus 1 is equals to 3, that is excited state is triplet. Thus, excited state are classified as singlet or triplets. The triplet state has the lower energy than the singlet state, in accordance with the Hund's rule. As already explained, O2 in the ground state is in the triplet state. It shows an exceptional behavior as the electronic transition takes place from triple ground state to triple excited state instead of singlet excited state. This is why the spectrum of O2 molecule is quite complex. The type of transition which certain category of compound undergo and the region or the wavelength absorbed for this transition are given below. First, saturated hydrocarbons or compounds containing CC and CH singlet covalent bond require very large energies to produce electronic excitation, usually beyond 160 nanometer, far in the UV region. In such molecules, pi to pi star transition take place. Second, a simple olefin has an absorption band at about 170 nanometer. In such molecule, pi to pi star transition takes place. Third, molecules like methylamine and methyl iodide which do not contain pi orbital undergo n to sigma star transition. Fourth, all electronic transition in organic compounds do not occur in the ultraviolet region. The occurrence of colored compound indicates absorption of radiation in the visible region. Compounds containing minus n is equals to n minus group or long conjugate system of double and single bonds, including aromatic ring, absorb at wavelength greater than 180 nanometer. That is why they look colored. Such groups are chromophores. In such cases, the energy of the molecular orbital lie closer together and pi to pi star transition takes place. Example, the protein beta carotene, a fairly large conjugated system, and show absorption at about 240 to 280 nanometer. Intensity of the electronic band. The intensity of any electronic band depends upon the extent of overlap between the wave function of the ground state and the excited state. Greater the overlap, greater is the intensity, as there is a very poor overlap of the wave function in the n to pi star transition, and there is an excellent overlap in pi to pi star transition. The intensity of the band produced by n to pi star transition is very low as compared to pi star transition. Further, in the presence of the acid, the electron of the n orbital undergo protonation and then n to pi star band disappears. This is for the electronic spectra. Thank you so much.